In this module, we will see how voltages are induced in PMAC machines and what the per phase equivalent circuit looks like and how we can control these machines. So in the earlier module, we saw that these machines are controlled by injecting currents into them, but as a consequence of injecting these currents, voltages are induced. And so we need to recognize that, and we'll see that these induced voltages under balanced sinusoidal steady state condition are caused by two reasons. One is that we have a permanent magnet on the rotor producing this B sub r space vector, and this is rotating past the stationary phase windings at a speed omega sub m. So certainly there will be induced back EMF induced in each of these windings. And similarly, we have this current space vector I sub s, which is producing its own flux density distribution, and that distribution is rotating past the stationary phase winding. So we again would have induced EMF in these phase windings, and the total induced EMF is really the sum of these two. So let's look at first the induced EMF due to the permanent magnets on the rotor, which are rotating at speed omega m. And this first equation is just to remind us what we have seen in previous modules. But in this case, we have a flux density distribution produced by the magnets on the rotor and given by the space vector Br. And therefore, the space vector representing the induced voltages in the stator due to this would be given by this space vector over here, where B sub r is over here, and the relationship is expressed by this equation over here. And we can see here that what we have is this induced EMF, which is proportional to the proportional to Br, and is related by this two factors. One is the speed omega sub m, and the other one is what we'll call in the quantities within this bracket as voltage constant Ke in volts per radians per second. And actually, it's more than this voltage it's more than this voltage constant Ke. But let's define this voltage constant Ke in volts per radians per second to be the same as this torque constant Kt, which we have seen in the earlier module, which was Newton meters per amp, and which had this expression over here. So if you make Ke and Kt the same, then this quantity within the brackets over here is 3/2 times Ke over here. So we get this expression here, which shows that this induced voltage space vector is given by this, and if you recognize J as being 90 degrees, we can take this J and instead of having just theta sub m here, we can make it theta sub m plus 90 degrees over here. So bottom line is that this induced EMF in the stator windings due to the permanent magnets on the rotor are related by the voltage constant and the speed of rotation here. Okay. Then the next thing we have to look at is the induced EMF in the rotor windings due to the fact that the current space vector is also rotating at speed omega sub m in steady state. And we have seen this equation before, where the induced EMF is 90 degrees ahead of I sub s over here. And so we can, again, making use of the magnetizing inductance, we can come up with this expression, of the induced EMF due to the stator current in terms of the stator current amplitude over here. Now, the net induced EMF is the sum of the two, and we are showing this under this optimum operating conditions where the current space vector is 90 degrees ahead of B sub r space vector as shown over here. All right. So we can see that in this case, due to BR space vector rotating at speed omega sub m, we have this induced EMF in the stator phase windings represented by the space vector. And then due to this current IS, we have induced EMF, which is also 90 degrees ahead of IS, given by this space vector over here. So the net induced EMF is the vector sum of these two, and that's this over here. So having seen, and this is mathematically expressed by means of these three equations over here, and having seen early on the relationship between space vectors and phasors, this is at space vector at time t equal to 0, let's say, and what various phasors would look like in phase A, the current phasor, the induced EMF due to the permanent magnets on the rotor, induced EMF due to this stator current space vector rotating, and the net induced EMF as a phasor in phase A. That can be represented by this diagram over here. So in this diagram, we add the leakage inductances which were ignored. So in a phase, we not only have the magnetizing inductance, but also the leakage inductance. So we can take that effect into account. And also we may have some resistance, R sub S. So this is in a phasor diagram, this is the induced EMF that we saw in the slide before, but to that we can add the drop due to the stator resistance and the leakage inductance over here, and come up with this applied voltage V sub A phasor. So knowing this from this phasor diagram, we can from these phasors we can come up with this per phase equivalent circuit as this is the voltage that has to be applied to supply this current over here, and then we have this back EMF due to the permanent magnets on the rotor. Then if you include the magnetizing inductance, which represents the effect of the fact that we have a rotating current space vector which is inducing EMF in the stator phase windings, we have this phasor, and to that we add the drop across the leakage inductance and the resistance in order to come up with the phase voltage that needs to be applied to get this current IA over here. So once again, we have, in order to see how what we need to do, let's look at this block diagram here, which shows that basically we are injecting currents IA, IB, and IC as a function of time, knowing the rotor position. And of course, these currents IA, IB, and IC have to be supplied in opposition to induced back EMF and these are supplied by this power processing unit, where the power is coming from, in most cases, the utility, but need not be, maybe through batteries over here. So in a very simplistic manner, we can show what is going on. Just let's take the case of phase A. This controller is telling us this is the reference current that needs to flow in phase A, and we can actually measure this current, and the difference of these two goes into this hysteresis block over here in this comparator to tell us what the switch position should be, and that is represented by these waveforms here. Let's say you want reference current which is in the middle of these two dotted bands that we see, and we can force this actual current in phase A to be within this band by controlling the position of the switch in this power processing unit. If the current goes above the top band, we change the position of the switch to be in the downward position, and vice versa. So by this hysteresis current control, we can get the desired currents to flow in this machine. But of course, there are much more. There are better ways to achieve this, but without and through power electronics. But without going into the details of that, for our purposes, it should suffice here. So here we have a very brief summary of what we have seen in this module. First of all, that we have induced EMFs in the stator windings, and we came up with the per phase equivalent circuit, and then we saw how we can supply, at least in a very simple manner, perhaps simplistic manner, currents into these three phases of this machine.